So I'm going to work through how we use energy balances, and specifically when do we use internal energy compared to enthalpy to describe the energy of a system. Let's start with the really basic energy balance that we always begin with, and that is that our energy into a system minus the energy out of a system equals the change of energy of the system. Now, the example I did in class the other day was a system I had like this, where I had mass flow in at one location. I had a possibility of boundary work here, so PDV work at this location, and then I had options to have heat in as well as work into the system. Electrical work, this could be spring work, this could also be shaft work. So these are typically when we write out work in, that's what we're referring to. So I'm going to specifically separate work in by these sources compared with boundary work. With this energy balance, we know that if the system is in steady state, then our change in energy of the system is 0. So this leads to energy in equals energy out. So that's our first major assumption we might make. If we don't have a steady state system, let's talk about what terms are included for each of these. If unsteady, which this case that we've drawn here obviously is an unsteady case. So the first case will be if there's no boundary work. So we're going to assume that this top piece is fixed, that piston's not allowed to move, and there's no boundary work. In that case, the things that are included, we have energy in minus energy out equals the change in energy for our system. In this case, the components of energy in include the total mass that flows into the system. Now here's where it gets tricky. This we use the enthalpy here, the enthalpy at that inlet case. And this is because if we think about the fluid flowing in, it's going to take some kind of a flow work to push that fluid into the system. So anytime we have a flowing fluid, we use the enthalpy because it has this flow energy that comes along with the internal energy when it's pushed into the system. Other ways that we can get energy into the system are our net work in and our heat into the system. The way that I've drawn it and defined my terms here, there's no energy out. That equals our change in energy of the system. The change in internal energy of our system plus the change in kinetic energy plus the change in potential energy of the system. And we typically, in thermodynamic systems, have no change in kinetic energy or potential energy of the system. So that's where we would get with this case. If we add in the boundary work, then in this first section here, so if there is boundary work, our energy balance now looks like we still have mass flow rate in plus its energy that it's bringing in. We have this net work in from electrical, shaft, and spring work. We have heat input possibilities. And then we also have the possibility of doing work on the fluid. So boundary work into a system is minus PdV generally, and then that equals the change in internal energy of our system. The trick here then is that if we have a constant pressure system, so often when we draw a piston cylinder system, we assume that this is a constant weight that's acting down, which means there's a constant pressure exerted on the system. So this integral then becomes PdV. P, the integral from the initial case to the final case. So V final minus V initial. And that equals the change in internal energy of the system, which was M final, U final, minus M initial, U initial. And this is where we sometimes end up in constant pressure systems, also seeing an enthalpy appear on the right-hand side, because if we move the boundary work over from a constant pressure system onto the other side, we end up with something that looks like the enthalpy. So I should have put that up here. Let me move that up. In this case, we're going to say, then we have this expression where we've simplified that integral, and then my equation becomes M in H in plus work in net plus Q in net equals M final U final plus P V final will be minus M initial U initial plus PV initial. In other words, these are enthalpies, H final and H initial. So hopefully that kind of clears it up. So there's actually two ways that I could have written it. In class, I wrote it out. I gave you this option as your possible correct answer, but actually it would have also been okay to have H's on both sides as long as we didn't keep the boundary work on the left-hand side. I'm going to do one more quick thing to help kind of solidify all of this. Let's run through the closed system options as well. We always start with our same energy balance. E in minus E out equals the change in energy of your system. Now this energy in and energy out for a closed system can only be heat and work interactions. Net work, shaft, electrical, spring work, those types of things. We could have net heat transfer into the system. We might also have boundary work in. Remember, all of these could be, if we put negative signs in front of them, they would be energy out. So I'm just choosing to use the convention that energy coming into the system here is positive, and I'm writing all of these as energy in. And then this is equal to the change in energy of our system, which is the internal energy, kinetic energy, potential energy. And again, for most thermodynamic systems, the change in kinetic energy and potential energy of our system will be 0. Again, we could write this out, including the boundary work, PdV work, and that equals the change in internal energy of the system. Again, if we have a constant pressure system, then the integral PdV becomes just P times the change in V, and this equation then looks like work net in plus Q net in minus P V final minus V initial is the change in internal energy of the system. And these pressure and volume terms can then be moved over to the right-hand side and look like an enthalpy term. So we have net work in plus net heat in equals the change in enthalpy of a system. So we also use enthalpy in closed systems when they're a constant pressure system. Either of these two versions of the equation are correct. Now, if we had a closed system and we had no change in volume, so if we have a constant volume system, if we come back up to this expression, work net in plus Q net in minus the boundary work equals the change in internal energy. Obviously, the boundary work is 0. Let me just write that out. Minus the integral of P dV, and that would equal 0. So that means that then we have an expression, work net in plus Q net in is the change in internal energy of the system. So for constant volume systems, we use internal energy. For constant pressure systems, we use the change in enthalpy. If we don't have either of those cases, we have to include the boundary work as an integral of PdV. Moving on to the case where we have an open system. Again, we start with energy in minus energy out equals the change in energy of our system. In this case, though, our energy in and energy out involve both heat, work, and mass interactions. So here we still have net work in plus net heat in plus boundary work in. And now we have mass flow in and the energy that it brings with it minus mass flow out and the energy that it takes with it. And again, we use enthalpy here because it's a flowing fluid and it carries with it what we call flow energy, or there's some energy required to push the fluid into the control volume. This would then equal the change in internal energy of the system plus the change in kinetic energy plus the change in potential energy of the system. Often these two are 0. Simplify that out. We can write out the boundary work as PdV work, and then we have the fluid coming in, the fluid leaving, and that equals the change in internal energy of the system. If it's constant pressure, then this PdV work might bring us an enthalpy term over here. That's somewhat rare in open systems, although the example we did earlier showed that option. So I'll leave it here for reference. You can refer to the constant pressure closed system to figure that enthalpy part out if you're unsure about that again. And then again, if we have a constant volume open system, which is often what we do, then we have work in plus Q in plus mass in. Enthalpy in is the change in internal energy of the system. So our boundary work here is 0. So hopefully that makes it a little bit easier to kind of see when we use internal energy and enthalpy. Let me highlight the important equations. So here's the most general form of the open system, including the potential for boundary work on the system in a not constant pressure or constant volume case. And then we have the constant pressure version, where the PDV term has been moved over to the right-hand side and included with the internal energy to create enthalpy. And then we have the constant volume system, which is perhaps the most common of the open systems, and that is the change in internal energy of the system. If we had a steady state system, of course, all of these terms on the right-hand side would go to 0. I hope that makes it clearer. Please let me know if you have any other questions. Good luck studying.